Swayam Prabha. Digital India. Educated India.
Good afternoon. Welcome you all to this next class, this particular course in analytical, spectral and microscopy applications of inorganic compounds and nanosystems. For the past two classes, we have been focusing on the aspects related to microscopy. We've just gone through some general introduction to microscopy. Then we started with the atomic force microscopy, which comes under the banner of the scanning probe microscopy techniques. And we have looked at the principle, and we have been looking at some examples towards the end of the previous class. Let me just browse through those examples once again. There are two modes, as I mentioned. One is the contact mode, other is the scanning, the tapping mode, which is more favored one, because the reason is that the tapping mode will not touch the surface. So either the surface as a sample or the tip or the probe do not get affected, and so therefore a lot of cases people have been using more. And you can also look at the surface of even in some catalytic kind of a systems. You can probe the top layer without any kind of a penetration into that, and you can also make sure that the tips are not being broken, tips are not being bent, etc., by using the tapping mode as compared to the contact mode. In the contact mode is a little more dangerous in terms of making some kind of a structural change or scratches on the surface and or to the tip as well. So that is where, so here, as you can see towards the end of this, in the tapping mode, you can study even small layers that are being put onto the top of any kind of a surface. For example, the lipid bilayers, adsorbed polymers on any surface up to about 0.4 nanometer thickness, or even those kind of a molecular layers which are stable for a certain period. So all these kinds of things can be done. The example shown here was for the plasmid, and you could see at two different pHs the difference in the plasmid structures itself, which gives both the XY as well as the height parameter. The AFM good thing is that you not only get the XY plane, but you also get the height parameter as well. So we've looked at some examples of the composites, so the nanocomposites. So here the nanocomposite is the ethylene methyl acrylate as the polymeric material, and the graphene oxide is the filler to that. So you can see at different ratios of the graphene oxides being filled into that, and you can find different percentages, the level of their homogeneity and as well as their roughness. So for example, here 1% of GO, 3% of GO, and 5% of GO, and 7% of GO. So as you keep going across these, you can see that these graphene oxides are more homogeneously being filled or being brought into the nanocomposite. So that is what you can evidence from this particular AFM microscopy picture, and as opposed to what you have at 1% and at the 3% cases that you. And if you go beyond this 5%, you can say at the 7, you would start seeing that there is a kind of a folding or a doubling of these graphene oxide layers, and which again makes it the system not so much useful for the properties that you are looking for. So these nanocomposites. So therefore AFM will give the characterization and a kind of a certification that yes, this is the kind of a distribution that you have, and this is the level of the roughness that you have. So it should not be too largely rough and too low, and at the same time the distribution should be as homogeneous as possible. For example, at this 5%, as you can see, I hope you are looking at this slide, and it gives a roughness of 13 to 15 nanometer, and the distribution, if you look at this one, perfectly well distributed. So therefore, whatever the properties you're expecting, you could expect a good output or out signal of such kind of a material. Now, as compared to the last one, the D, which is 7%, the 7% is completely flooded with these the folded or aggregated or double kind of these graphene oxides. So therefore, this will not serve the purpose of making it, and this also gave huge amount of roughness in this. So that's how the AFM helps a lot in these things. Further properties can be studied, etc. This is another example where you have a chitosan, again a polymer, the carbohydrate based polymer, into which you are looking at the silver nanoparticle. So here you can see the silver nanoparticle and the chitosan with the silver nanoparticles, and where you have several silver nanoparticles being embedded. Now, if you look at this view of the D and E, are the three-dimensional views. So the three-dimensional view, you can see the way that they are distributed, and this will also provide the roughness that you have, the distribution range. So all of these. So this is scanned over 5 by 5 micron, and this shows a 2 nanometer and the 5 nanometer, kind of a roughness. So the 2 nanometer you will get for the simple chitosan, sheet, and when you embed to this kind of a level of these silver nanoparticle, then it will go to the 5 nanometer one. So these kind of things give the topographic patterns of the nanoparticles, and these comprised of various levels depending upon the doping, depending upon the extent of the silver nanoparticle nanofiller done. You can reach to the levels of 0 to 70 nanometers, and with the side lengths of from 1 to 3 to about 4.5 micron. Okay, so these kinds of things will provide. Now you can see in the F give you the heights of the particle or the roughness of the nanoparticle. Here in this particular case, so these are within the 100 nanometers level in the chitosan matrix. So now looking at what kind of a property you require. In this particular case, this was made to increase the thermal stability. So therefore, you can study at different loadings, and each loading, the AFM gives you the certification, how it is distributed and what level of nanoparticle size, and then also the roughness, etc. And then you can go and look at the thermal stability as a separate experiment, and then you can try to correlate between the structures which are obtained or information that is obtained from the AFM with that of the information that is obtained from the thermal stability. So that is how these AFM can help in preparing for better materials, better nanocomposites, etc. in that. We also have seen towards the end of the previous class that taking epoxy based material, making a nanocomposite, this TBD is epoxy material, 3% of exfoliated graphite, and these are the top 3 are for this particular composite, and the second composite is the epoxy plus the carbon nanofibers, 1% here, and that is the bottom one. So in both the cases, the AFM has given or measured using the AFM. One is the height based pattern, other is amplitude based pattern, and the other is phase based pattern, all the 3. So all the 3 will give the corresponding parameters in that. Okay, so the height base will give you the kind of a shapes that you have, and the amplitude will give you kind of a topology that you have, and these kind of fixtures of phases, what kind of a different phases, topology, as well as different kinds of phases if you have in the composite, whether they are all uniform phases, all these can be identified. So using just these, so the amplitude, So using this, you can provide the lateral and height dimension, the amplitude in the tapping mode and deflection in the contact mode. Often shows the sample with sample shapes, and the change in the oscillation amplitude, which is got obtained in the second one here in this particular picture, and this gives the surface topography. And the phase image, the last one, shows how the phase of the cantilever oscillation is influenced by the interaction with the surface and provides information on the local stiffness. So this kind of an information this kind of a picture can give you the topography with stiffness regions. So, and stiffness, less stiffness, etc., the regions of that. So you have three different kinds of AFM pictures giving three different nature of information. Together will make the material and then understanding of that. Okay, the shape, the topography, and the physical parameter or mechanical parameter of the stiffness of zones. So now you can see that where the stiffness zone and the less stiffness zones, etc., and how their topological features you can map from this to this, and their shape, etc., all of these. So this is the kind of information that one will get. So in this, the AFM technique, through the capture of the height is the first one, the amplitude, the middle one, and the phase data, and in the last one, allows the surface structure and the material domains to be directly compared. So in conclusion, AFM morphological investigation demonstrate that the good levels of carbon nanofiller, in these cases, dispersion into the epoxy mixture improves the properties of the nanocomposite and also the curing process. Okay, so and this is done for the epoxy with the exfoliated the graphite, and this gives for the epoxy within carbon nanofibers. So three different types of things, not one AFM. So AFM getting from the height wise, the amplitude wise, and the phase wise. If you see the scale, you can see this is in the nanometer, this is in the millivolts, and this is in the degrees. So phase wise. So phase comes from the degree, orientation things, and this potential difference gives you the topological things, and this will give you the shape or the height of the parameter. So these are the kinds of things that are very helpful in comparing this with the properties that you have. So if you have more regions of stiffness, you can talk about measure the mechanical stiffness and compare with different things. You can make different fill levels of this, measure their AFM, measure their stiffness, and then compare, or mechanical parameters. You can connect with, as I told in the previous class, you can measure the mechanical properties, Young's modulus, etc. You can measure the strengths, tensile strength, mechanical strengths of these ones, and you can measure the conductivity, you can measure the charge flow, you can measure these potential differences. So variety of parameters can be there, and for each of these you can map it, the whole, whatever the sample you have on the surface. Okay, and that's what is more details are given on this particular slide. And AFM can also be used for a large number of, just now I told, all those are engineering applications. So let us look at one engineering application of a polymer by AFM. Okay, so you can investigate the surface mechanical properties including Young's modulus, adhesion, viscoelasticity, energy dissipation, all these kinds of things in this, okay, as a mechanical mapping. So therefore the AFM is used largely by engineers from the mechanical side, material side, the electrical side. All of these people use a lot for their materials to characterize and thereby compare with the kind of the property that they are projecting, and then make a correlation between the AFM giving the regions versus the property, and therefore you make a correlation of that. The ability of nanomechanical mapping for identifying the composition and evaluating the mechanical properties at nanoscale will open a new way to study surface properties and explore microstructure property relationship. This is what just now I mentioned, that they talk about the structure and the property relation, and that will lead to the application domains, the expands. And I already explained to you in the previous class variety of application domains are there for AFM. It's almost unlimited kind of application domains. Okay, let us look at one example. Here it is used the tapping mode. In some cases I have not mentioned, but it's not very important. You take it as, because you're looking at analytical way, you're comparing and expecting that all of them are done at the same kind of a mode. So therefore there is no problem. So AFM tapping mode pays images of NR5, NR20, NR60 nanocomposites. What is this NR? NR is a natural rubber. If you want more details, I have given always this particular paper where I have taken from. So you can go through this. You will get not only the information from the AFM, you will get other characterization information too, other supporting information as well. If you are interested, you can always look at that. And not only for this, for everywhere I use the same kind of thing. So the references are always available. So the natural rubber with multi-walled carbon nanotubes, MWCNT, multi-wall carbon nanotubes. These loadings are done at 1, 3, 5, 10, 20, 60. The PHR is parts per 100 rubber. So that means 1 part for 100 parts of rubber. 1 part for 100 parts of the rubber. That's how they use, like parts per million and parts per billion. Here parts per rubber. So parts per 100 rubber. Okay. And so there is 1, 3, 5. These are all made and prepared using a 6-inch 2-roll mill. So after making, they will take through the roll mill and then make sort of a flat and then use a small film of that for studying this one. And these are labeled as NR1, that means with 1 loading, NR3 3 loading, NR5 5 loading, etc., etc. The micrographs which are shown here are only for 3 cases. There is 5, 20 and 60. The 5, this is for 20 and this is 60. So if you look at these, you can see the fillers of these multi-wall carbon nanotubes. You can see like that fillers here and a little bit more dense and much more dense with more, also some kind of a homogeneity is also got increased here when you come to the 60. Shows relatively homogeneous dispersion. And so these showed somewhat less loading, and you have a little bit of better loading, the dispersed, especially low CNT, and very high loading content. The CNT shows relatively homogeneous kind of a dispersion. So the homogeneous dispersion, when you go for further properties of this rubber, which is made in nanocomposite with the multi-wall, the carbon nanotubes, you're looking for the strength of that. You're looking for some properties like bending and other things. So all of these are very important. Okay. So therefore their distribution is very important, their picture, how they are distributed in the surface by using the AFM. So the fair dispersion of the pristine CNTs can be attributed to the high shear stress exerted during the mixing. So what you do is you mix these things and you take them through those roll mills. So that is where the compound gets very distorted by the large shearing force when it passes through the roll mill. Okay. So however, the rubber's recovery, because again there is a recovery process also when it comes out of it, the force occurs immediately after passing through the roll. So by this is called the kneading process. They repeat that. Okay. So this distortion, recovery, distortion, recovery. So it is thought that the CNTs are taken from the cohesive group, thread by thread kind of thing, and then are homogeneously dispersed. So when you mix it in the rubber, it is in somewhat like a fluid state, somewhat semi-fluid state, and this you take through this mill and you apply a force and then you try to put that kind of a force through that. Then it presses, then when it comes out, relaxes, again take it through that a few times to make into the homogenized. How do you know it is homogenized? If you look at this particular, the AFM, the micrograph, you will be able to make out the surface how homogenized. So here it is filled but not homogenized, less filled bit more but less homogenized, and somewhat okay but not less homogenized, much more homogenized. So therefore you will have a uniform kind of an property that will be shown by these kind of things. So the AFM is just not simple characteristic, but it is a kind of a certification technique that yes, this is going to give a better property for you. So that's kind of a thing. I hope you understand that nanocomposites of all of these. Before we go to the other techniques, let us look at another example. We talked about the AFM can be used combined with a lot of engineering, particularly mechanical. Example I've taken. I have not taken the example for conductive AFM, which is called for the charge conductance, etc., which mostly electrical people use. I have not taken that example, but you can use that as the exercise I will give you in that. So here, this is the Young's modulus distribution. From the AFM, you can convert into the Young's modulus and then make a plot, and that is what is the Young's modulus plot of NR20, which you have seen already in the previous slide, that NR20 sample, and Young's modulus peak values of the nanocomposite. So AFM magnified regions of Young's modulus and adhesive map. So this is the B, which is the adhesive map. So, and this is the one which is the Young's modulus. So you can see the regions with differently colored regions. So the ones which are light green, kind of a shaded color, the light green areas show higher adhesive energy but lower elastic modulus. So lower elastic modulus, that means you have more of a rubber region, that one, less of the multi-wall carbon nanotubes. What it means is, so the regions you can easily make out, the green regions of that. Thus the nanomechanical mapping through AFM is successful for identifying and characterizing the heterogeneity or homogeneity in the nanocomposites containing various components. In this case, the rubber with the multi-wall carbon nanotubes, how homogeneous, how heterogeneous kind of things, and the regions of elastic and etc. Now, by comparing the scale of the adhesive energy and Young's modulus, so this one is the adhesive energy levels, okay, and the Young's modulus map, these ones of different samples, it is noticed that with the increase in the carbon nanotube loading, the greater the loading, that means you have the 5, you have 20, then you have 50, you have 60, etc. So the greater the carbon nanotube, multi-wall carbon nanotube loading, the adhesive energy gradually decreases and the Young's modulus increases. The reason is you get regions of more accumulated, the nanotube regions will come. They will give a strong or higher Young's modulus, but they will not have a strong or very high adhesive energy. So therefore, so if you want to increase the Young's modulus, so you go for higher loading. If you want to have more of an adhesive energy, if you're applying for the adhesive, like means if you're using for some the gum tape kind of a applications, then you go for the adhesive energy. More adhesive means more sticking kind of a property. So therefore you can use, so you can go for the less loading. And if you want to use for a strong film kind of a thing, then you need more Young's modulus, then you go for greater loading. So now it can tell you the AFM converted into the Young's modulus map and the adhesive map will tell you what kind of an application that particular composite will be suitable or useful. That is where you can get the information. So as comparison, Young's modulus histogram of the NR20 sample and the peak values, you can see that this is for the NR20 sample. So you can see that as the carbon nanotube composition and this Young's modulus is increasing, and that's what we said. The greater the loading, the greater the Young's modulus, but less adhesive. So if you're looking for a sticking purpose, look for the adhesive property more, less of the Young's. You don't require there to be strong. Okay, it should be more flexible, more sticky kind of a thing. So that is where you can see. And another thing is also shown, the deformations of these. Okay, the deformation and the force, and that force is nothing but the adhesive force. So adhesive forces at for the multi-wall carbon nanotube and interfacial region, at the fully multi-carbon nanowall region and the interfacial. That means between the region of rubber and this particular the carbon nanotube, that is what is interfacial. And NR is natural rubber. 3 regions are there in the whole sample. So mostly the green, as you said, is mostly the region of natural rubber kind of thing, and there is more rubber, and these ones are where you have the carbon nanotube region, and the somewhat little grayish or yellowish one is the interfacial kind of thing. So you have the carbon nanotube, interfacial, and the bulk, which is your rubber. So you can get the whole mapping of that. So that you can get the multi-wall carbon nanotube, interfacial region, and NR region. NR is the natural rubber region. So using these kind of maps, you can decide the material, its quality and utility, etc. in all these things. Okay. So these are some examples. Of course, I will give you towards the end of the microscopy thing. Then I'll give you the topics where you can have your own attempts to understand the things. I could not cover possibly all the examples in this. Okay, we will now enter into another domain. This domain is based on the electron microscopy. So far we have seen that the microscopy is touch and feel and give the signal. That's what it is. Touch and feel. So the touch and the feel is the interactions and the signal, and that's what we are doing. In the electron microscopy, let's say, you already know earlier when you were studying the spectroscopy, I have shown when the light is incidented on the matter, what are the things that could happen. Similarly here, it is the electrons, when they incident on the matter, what all could happen. So that is where these things. So interaction of electrons with matter. I draw your attention to this. You can see that if you take this as the matter and different regions are shown, and this is where your electrons are pumped in, which is called the primary beam. So your electron is pushed onto the sample, and many things happen. So many things happen. We know some of the things already earlier, and some of the things could be. One is the electron that you pumped in can pass through completely and come out, and that's what is the transmitted electron. And the electrons that you have put in can be back scattered. So without doing much, without touching any of your atom or molecule, they go through the regions which are no electron density kind of thing. Or they can hit another electron in your valence band or even core, and then knock out that electron. That is what is your secondary. And where did we study this? This we have studied already in the photoelectron spectroscopy. I have already given that spectroscopy thing. And there I have also talked to you the secondary process of the next process is the Auger. That also I have talked, though we have not covered the Auger spectra, but we have covered the electron spectra, so already in that. And there I also mentioned when an electron coming from the upper drops down, there is an energy coming out. It could be in the X-ray radiation, or a light wave can also come, which is called luminescence. So all of these, fluorescence, the luminescence, so all of these. So many different kinds of processes, or there can be a diffraction, because different waves coming out can overlap and give you the diffraction. That is what, from different centers of the atoms in that. So diffracted electrons, transmitted electrons, secondary electrons, backscattered electrons, etc. So of these, the energies will differ. The primary will have the highest energy, all others will have a lower, and therefore huge range of domain of the energies. So you can never easily measure all of these using in one instrument. You cannot have a captured detectors for all of them. So just to give an example, the primary electrons, okay, knocking out the secondary electron. And this is what is measured in case of the scanning electron microscopy. The primary electron beam does not touch anything, goes out, is backscattered, whatever the thing comes and goes out. Will be very little difference in its energy. So that means it is still very highly energy. Then other thing is, when you have knocked an electron, gone out, another electron coming into this, and then this difference in the energy comes as a characteristic X radiation. Okay, and of course I have not talked about the X-ray fluorescence, but I have just given an idea of that even earlier as well. And these are so different processes. So one can study using the transmitted, it's called TEM, transmitted electron microscopy. these secondary electrons, which can give you the scanning electron microscopy. And these are the two which we will try to cover in this particular topic as the next ones. Okay, so we'll start with that in the next class and go through the process of TEM and the process of SEM. And with that, we will be covering at least 2 to 3 more classes. We will be focusing in this microscopy part of it. Thank you very much.